Imagine trying to blow up a really heavy-duty rubber balloon.
Okay.
Initially, you push some air in and it expands pretty easily.
Right, just normal inflation.
Exactly. But the more air you force into it, the harder that thick rubber fights back. Like the tension just builds.
Mm-hmm.
And eventually, the rubber itself stores so much energy that if you let go, it would just violently snap back.
Oh, absolutely.
So for over a century, we've kind of thought of our universe as the complete opposite of that balloon. I mean, we've treated space as this totally free, empty void that can just expand infinitely without any effort.
Or any resistance at all, yeah.
Right. But there's this groundbreaking new physics paper that's suggesting the vacuum of space might actually be fighting back.
And that is a profound shift in how we understand the cosmos. Welcome to the deep dive, everyone.
Yes, welcome.
Looking at the research in front of us today, specifically this fascinating paper titled Geometric Elasticity of Spacetime, we are really questioning the foundation of modern astrophysics.
We really are.
We're asking, what actually happens when the fabric of reality is stretched?
And as always, I'm thrilled to be exploring this with you, sitting across from your very intimidating backdrop of star charts and dense mathematical chalkboards.
Well, I try to keep it atmospheric.
It's working, because to understand where we're going today, we first have to talk about where physics has been since Einstein. So,
Okay.
let's unpack this. We're usually taught that space-time is this dynamic stage, right? And its main trick is that it bends.
Right. Curvature is the absolute bedrock of general relativity.
Okay.
You place a heavy star or like a whole galaxy on that stage, and the floor warps under its weight.
And we feel that warping as gravity.
Exactly. It dictates how planets orbit, how light bends around massive objects, all of it. But, and this is key, that beautifully elegant picture carries an underlying assumption.
Which is what?
It assumes bending is the fundamental and perhaps the only way the universe reacts to matter and energy.
I see. I mean, most of us have seen that classic high school physics demonstration, right?
A rubber sheet.
Yeah. The teacher stretches out a rubber sheet, drops a heavy bowling ball right in the middle, and it makes this deep bowl shape.
Right.
And then they roll a marble around the edge to show how gravity pulls things into orbit.
It's a great visual.
It is, but that analogy really only cares about the shape of the dip. Like, it completely ignores the physical material of the sheet itself.
Oh, that's a really good point.
So let's take that a step further and look at, say, a trampoline.
Okay, a trampoline.
When a heavy person stands in the center of a trampoline, yes, the mat dips down. But if you look at the edge, the metal springs are physically elongating. They're under immense tension, like pulling back against the stretch.
Let's run with that trampoline analogy because standard cosmology has essentially been ignoring the springs.
Wow, really?
Yeah. I mean, we know for an absolute fact that the universe is expanding. We observe galaxies drifting apart, and the vast cosmic voids between them are, well, they're physically growing larger.
Right.
And the formal term the paper uses for this is volumetric deformation.
Volumetric deformation, meaning the actual volume of the universe is changing. The literal box is getting bigger.
Correct. But conventionally, physicists have treated this expansion as merely a kinematic process.
Meaning just, what, motion?
Exactly. Just a description of motion over time, like watching cars drive away from each other on this infinitely stretchable, completely free highway.
Okay.
But the new framework we're diving into today proposes that this expansion is actually a geometric deformation of space-time itself.
Oh, wow.
And just like those trampoline springs, when you deform a material, there's a real, calculable, energetic cost.
Okay, so if space acts like a physical material that actually resists being stretched, we have to find a way to measure that resistance, right?
Aye.
Because you can't exactly hook a cosmic tape measure up to the vacuum of space. So how do physicists quantify the hidden tension of the universe?
Oh. Well, that requires building a new mathematical structure right on top of general relativity.
Okay.
The authors of the paper introduce what they call a dynamical time-like vector field.
A vector.
Yeah. Imagine assigning a tiny arrow to every single coordinate point in the vacuum of space.
Literally a field of arrows everywhere.
Everywhere.
So they have a magnitude and a direction. What are they pointing at?
They're all pointing along the local flow of cosmic time.
Oh, time, not space.
Right. And by doing this, they establish what is called a local cosmological rest frame. It basically gives the universe a geometric reference direction for time.
Here's where it gets really interesting, because once you have an arrow sitting at every single point in space, you can watch what happens to them as the universe expands.
Exactly.
The paper introduces this concept called the expansion scalar to track this. So if I'm looking at a cluster of these arrows and the universe expands, those arrows are going to start drifting apart.
Yeah, the expansion scalar is measuring exactly that divergence.
Okay.
If the arrows are moving away from each other, your scalar is a positive number. Space-time is stretching. If you're pointing inward and converging, it's negative, meaning compression. And if they just remain perfectly parallel, the volume is unchanged.
Right. So we have a mathematical tool to track the stretch. But a stretch isn't just a measurement. It requires energy.
Right.
And I noticed the paper mentions this concept works in a covariant way. I see that word thrown around a lot in physics, and, well, it usually means the math plays nice with Einstein.
Yeah, that is a crucial detail. A covariant theory means the laws of physics remain consistent for all observers, regardless of their frame of reference.
Okay.
So whether you're floating completely still in the intergalactic void or you're zooming past it near the speed of light, the mathematical description of this stretching space-time remains entirely valid.
So there's no privileged perspective.
None at all.
Okay, so the math is solid from any angle. But how does the physical tension actually build up? Like, how do those separating arrows generate energy?
Think about an invisible rubber band connecting every two adjacent arrows in our vector field.
Okay, visualizing that.
As the universe expands and that expansion scalar goes up, those arrows pull apart.
Right.
So the invisible bands stretch, and they start storing potential energy. And what's fascinating here is how this perfectly mirrors classical material science, specifically Hooke's law.
Hooke's law. That's springs, right?
Exactly. In standard mechanics, an elastic system stores energy proportional to the square of its deformation.
Like pulling a bowstring. If you pull it back twice as far, it requires 4 times as much effort.
Right.
And it stores 4 times as much energy. So the paper is taking that very grounded, mechanical principle and scaling it up to the entire cosmos. Space-time stores elastic energy proportional to the square of the expansion scalar.
Which fundamentally rewrites our understanding of the cosmic timeline.
Yeah, I'd say so.
Because expansion is no longer a free ride. As the universe stretches out over eons, elastic energy is constantly accumulating in the very fabric of the void.
Okay, so the math says stretching costs energy. But energy doesn't just sit there doing nothing in Einstein's universe. Energy creates gravity. Mass and energy are 2 sides of the same coin, and both warp the stage. So what does this all mean for the actual cosmos we observe? Like, if this elastic tension is constantly building up everywhere, shouldn't it be doing something massive to the universe around it?
Oh, it does. It creates an unavoidable feedback loop.
Okay.
As the universe stretches, elastic energy accumulates. And because any form of energy contributes to the gravitational field, this newly accumulated tension generates an effective stress energy component.
Okay, in simple terms.
In simple terms, the built-up energy from the stretch starts behaving gravitationally, which directly modifies how fast the universe accelerates.
Wait, hold on. Let me push back on this.
Go ahead.
We already have an explanation for what accelerates the expansion of the universe. Standard cosmology uses dark energy.
Right.
We've spent decades measuring it, and we usually represent it with a cosmological constant, specifically an equation of state parameter equal to -1. If I understand that correctly, normal matter has a positive pressure that pulls things together via gravity, but that -1 means dark energy has a negative pressure it pushes outward.
Exactly.
So are you saying this paper completely tosses out that dark energy fluid?
It offers a completely natural alternative.
Wow.
Because in our standard models, we basically just tape dark energy onto the side of Einstein's equations.
Right, like a patch.
Exactly. We see the universe accelerating, so we add that -1 constant to make the math balance out. But we don't actually know what that ghost fluid is.
Nobody does.
But in this new framework, you don't need to insert a mysterious external substance. The energy driving the outward push emerges directly from the geometric tension of space-time itself.
Because the elasticity of space-time is the thing pushing back.
Yes, the universe is acting as its own engine.
That is wild.
All right. But to address your pushback, the model doesn't just recreate a static constant, it creates a dynamical equation of state.
Dynamical, meaning it changes.
Yes, the elastic response evolves over cosmic history.
And that is exactly where I get stuck.
Why is that?
Because if space-time elasticity is dynamical and constantly changing, wouldn't our past telescope measurements have already caught those fluctuations? I mean, we look at ancient supernovae, and dark energy seems pretty static to us. How does this theory explain away the fact that dark energy looks so constant?
That is the beauty of the mathematics in this model. While it is dynamical early on, as the universe expands and the elasticity builds, the system naturally approaches what we call a de Sitter state.
Okay, let's define that for the listener.
Yeah.
What physically is a de Sitter state?
A de Sitter state is a model of a universe that is completely empty of ordinary matter and dominated entirely by a positive cosmological constant,
Okay.
or in this case, dominated by our elastic energy. It results in a steady, exponential expansion.
Steady expansion.
Think of it like a skydiver reaching terminal velocity.
Well, that's a good way to picture it.
Right. Early in the jump, their acceleration is changing rapidly as wind resistance builds up, but eventually, the forces balance out and they fall at a constant rate.
I see.
The elasticity of the universe evolves until it locks into this steady de Sitter state, which perfectly mimics the static dark energy we observe in telescopes today.
It mimics it today, but implies a wildly different past.
Exactly.
Which actually brings us to one of the biggest crises in modern physics right now, the Hubble tension.
Yes, the Hubble tension.
We have two different ways of measuring how fast the universe is expanding, and they're giving us two completely different answers.
Right. The early universe measurements taken from the cosmic microwave background.
Which is the afterglow of the Big Bang.
Yes. Those give us a slower expansion rate. But when we look at the late universe, measuring the light from relatively nearby supernovae, the expansion rate is faster.
And they just don't match.
No, they don't.
It's like having two different speedometers in the same car, hooked up to different wheels, telling you you're going two different speeds.
That's exactly it. And this elastic theory introduces a mechanism that could resolve that discrepancy.
Really? How?
Because this elastic energy acts gravitationally, it effectively modifies the gravitational coupling on very large cosmic scales.
Modifies the coupling.
It essentially renormalizes Newton's constant, the fundamental G in our gravity equations.
Okay, let me see if I have this. It's like looking at a magnet.
Okay.
Up close, measuring the expansion of the universe right nearby using supernovae, the magnet behaves exactly as standard math expects. But if you pull back and look at it across the span of the entire cosmos, using that background radiation, the background tension of space itself makes that magnetic pole look slightly weaker than the math says it should be.
That captures the mechanism perfectly.
Wow.
The strength of gravity is subtly shifting depending on the scale you look at. This provides a purely geometric reason for why our early universe and late universe speedometers are misaligned. It shifts the cosmological inferences.
I mean, we are throwing out a lot of established cosmology here.
We really are.
We're replacing dark energy with cosmic tension, and we're tweaking Newton's constant on a massive scale. And usually when you mess with Einstein to this degree, the math just breaks down and creates monsters.
Yes, it does.
Does this theory actually hold up to scrutiny, or does it fall apart when you poke it?
Well, this raises an important question. Any new modified gravity theory has to pass a rigorous stability analysis. Many beautiful theories fail because they introduce what physicists call ghosts.
Like literal physics poltergeists.
Basically, yeah. In quantum field theory, a ghost is a particle or a field that has negative kinetic energy.
Wait, negative kinetic energy?
Yeah. Imagine throwing a baseball, but the faster it moves, the less energy it has.
That makes no sense.
Right, and if you try to slow it down by catching it, it actually gains energy.
Okay, that sounds like a recipe for disaster.
It creates a runaway instability. The system would just spontaneously generate infinite amounts of energy, violently amplifying every tiny vibration until it literally tears the universe apart.
Well, we definitely don't want that.
No. A viable theory must strictly avoid ghosts. So the authors of this paper conducted a perturbative stability analysis.
Meaning they poked it.
Exactly. Meaning they introduced tiny ripples or perturbations into their mathematical model of the cosmos to see if they would blow up out of control.
And the verdict? Because I prefer my universes completely intact.
Stable regions of parameter space absolutely exist.
Oh, good.
The universe remains perfectly intact as long as the elastic coupling is positive.
Meaning what, physically?
Physically, that means space-time naturally resists deformation. It pushes back against being stretched, behaving exactly like a stable physical material should, rather than amplifying the stretch out of control.
Okay, stable materials resist stretching, but let's go back to our trampoline mat.
Okay.
Even the absolute best, most durable rubber in the world will eventually snap if you pull it too far.
Right.
There's always a breaking point.
Sure.
So if space-time is expanding and it acts elastically, does the universe have a snapping point? Like, can space literally tear?
If we connect this to the bigger picture, the mathematical framework suggests something even stranger. It introduces a concept called holographic saturation.
Holographic saturation.
Space-time doesn't snap like a physical rubber band. Instead, the expansion strain is bounded by a maximum possible value.
A hard limit on how much space can stretch. What decides that limit?
It's tied to the Planck scale.
Ah,
This is the absolute smallest, most fundamental scale of reality in quantum physics. Once you zoom in past the Planck length, our classical understanding of space and time breaks down into quantum foam.
right.
As the geometric strain of our expanding universe approaches this Planck scale limit, a new phenomenon emerges: geometric pressure.
The paper calls this an ultraviolet or UV cutoff, which, to be honest, always throws me. Like, why are we talking about sunlight when we're talking about the fundamental fabric of the universe?
It's just a classic physics naming quirk. When physicists say UV cutoff, they aren't talking about sunscreen or sunlight. In physics, shorter wavelengths of light, like ultraviolet, carry higher energies and represent incredibly microscopic scales.
Okay.
So a UV cutoff just means there's a hard mathematical wall at the absolute smallest, most energetic scales, a point where you simply can't zoom in, or in this case, stretch any further.
Oh, I see.
The fabric of reality stubbornly refuses to thin out past that limit. The geometric pressure acts as an immense resistance.
Man, it's such an incredibly elegant solution. But beauty isn't proof.
No, it's not.
We can't put the universe in a giant laboratory vice grip to see how far it stretches. So how do we test a theory that operates on the scale of the entire cosmos?
We look for the subtle fingerprints it leaves behind. And the theory makes several highly specific, testable predictions.
Like what?
First, because the dark energy equation of state is dynamical. The way massive cosmic structures like giant webs of galaxy clusters grow and clump together over billions of years would look slightly different than what a static dark energy model predicts.
Because the background elasticity is subtly changing the gravitational rules as those galaxies assemble.
Exactly.
So if we map out where all the galaxies are, we might actually see the tension in the web.
Right. Additionally, gravitational waves, the violent ripples in space-time caused by colliding black holes,
Yeah.
they might acquire very small, measurable corrections as they propagate through this elastic medium, rather than just empty vacuum.
Wow.
We'd also expect measurable shifts in the cosmic microwave background.
But are we waiting 50 years for the technology to actually see those fingerprints?
Not at all. We are on the cusp of it right now. Next-generation surveys are already coming online.
Really? Like which ones?
The Euclid Space Telescope, the Dark Energy Spectroscopic Instrument, or DSI, and the Vera C. Rubin Observatory.
Okay.
They're gathering data with unprecedented precision. Over the next decade, these instruments will have the sensitivity to map the history of cosmic expansion so accurately that they could actually distinguish between a flat, static cosmological constant and the evolving dynamic signature of geometric elasticity.
So, if you've been following the ongoing drama and debates in cosmology, know that we might actually have an answer within our lifetimes.
We really might.
We've covered a staggering amount of ground today. We started with the familiar picture of space-time bending under the weight of stars, and we've walked through the math of how space might actually stretch, tracking vectors and expansion scalars. The takeaway here is profound. What we've been calling dark energy, this mysterious, invisible fluid making the universe accelerate, might not be a separate substance at all.
Yeah.
It might simply be the universe's own inherent elastic response, pushing back against its own expansion.
It's a brilliant paradigm shift. But, as with all theoretical physics, we have to respect the scientific method.
Of course.
The theory is young. The authors have significant hurdles ahead before this becomes textbook science.
What's the biggest hurdle?
Well, they must establish precise observational constraints using the data from Euclid and DAI. And they have to study nonlinear structure formation.
Meaning what?
Meaning, they need to prove the math still works when matter gets incredibly chaotic and dense, not just in the smooth, empty vacuum.
Ah, okay. They also have to prove its quantum consistency, right? Which is kind of the white whale of all gravity theories.
Indeed it is. And, perhaps most dauntingly, they must explore what this elastic spacetime means for black hole solutions.
Which actually brings me to a final thought I want to leave you with today.
Okay.
We've talked about the whole universe expanding outward, eventually hitting that geometric ceiling at the Planck scale where geometric pressure refuses to let space stretch any thinner.
Right.
But what happens in the most extreme, localized environments in the universe? Think about a supermassive black hole.
Okay.
It's a singularity of near infinite density, literally dragging space-time down with it. If space-time acts like an elastic material, what happens if an incredibly dense object violently stretches local space-time to its absolute maximum limit from the inside out?
Wow. That is a staggering thought experiment.
Right, because if space can't snap, and it hits that hard holographic limit where it just refuses to yield, what does it do?
I mean,
Could that resulting elastic rebound, that intense localized pressure, create entirely new, unobserved cosmic phenomena?
that's fascinating.
Could black holes be sitting on a coiled spring of geometric tension, generating sparks of energy or new forms of radiation we don't even have a name for yet?
It's entirely possible.
It's definitely something for you to ponder the next time you look up at the night sky.
Absolutely.
Thanks for joining us on this deep dive.